And we really have to move on, I'm very sorry, to our next speaker, Cees Bassa from Astron, the Netherlands Institute for Radio Astronomy. Cees is going to share his slides online, hopefully, if he is. Yes, I think he is on. Cees, can you hear us?
Yeah, I can hear you. Can you hear me?
Yeah, take it away.
Okay. Thank you for allowing me to talk remotely at this conference. Unfortunately, I couldn't be there, but I'm glad that I can show the results that this team of people shown here have been able to complete recently. So the results I'm showing are published in this paper led by Federico Di Bruno. And Federico is the lead author, and some of the other authors like Benjamin Winkel and Josh Kula are actually at the meeting. So any questions, you can also ask them in person at the meeting. So the previous two talks spoke about intended emission that satellites like Starlink and OneWeb emit, the emission that is used for the downlink of broadband internet. But we became worried that if there's a large constellation of identical satellites that any electronic equipment on board will generate unintended electromagnetic radiation that could also be picked up by telescopes. And that's what we set out to try to hopefully not measure. Unfortunately, we do measure it. And the telescope we used for that is the LOFAR low frequency array. This is a telescope in the Netherlands, but it has stations spread throughout Europe in the country shown on the right. Shown on the left is the central core of LOFAR, which has the highest concentration of stations, and it's made up of two types of antennas. We have the low band antennas, which are basically drain pipes with wires at 45-degree angles for covering the frequency range from 10 to 90 megahertz. And so to put this in perspective, for frequencies below 10 megahertz, basically the atmosphere no longer is transparent, so we can't detect radiation above that, below that. And then from 90 megahertz upwards to 110 megahertz, there's the FM radio signals that you can listen to with your car radio and things like that. So we avoid that by designing our antennas such that they have no sensitivity there. And then from higher frequencies, we use these high band antennas, which are grouped in arrays of 4 by 4, making up 24 of these tiles here and 24 of these tiles here. So this is one station. And then here we have 6 stations, and you can see some more stations at my cursor locations. And this makes up for a lot of individual antennas that are then combined into one large telescope where we can look at the sky. The regular radio telescopes that are of the dish shape, they point by just mechanically moving the telescope. With LOFAR, we have no moving parts. So instead, we form beams on the sky by combining the signals from the individual antennas using delays between the antennas. And so we do that within an HBA tile to form a tile beam, which has a field of view of about 20 degrees across, full width half maximum. Then if we combine the signals of the tiles within a station, we can go to something that has a field of view of 5 degrees full width half maximum. And then for the observations we've done here, we've combined the antennas from the SuperTerp. That's basically these 12 HBA stations. And those beams then are a size of 24 arc minutes, so a quarter of a degree, or about half a degree. And with this configuration, we've basically tiled the main beam of the telescope, which is shown here. This is the sort of 5-degree field of view of the telescope with 91 of these smaller tide array beams. And for comparison, this is the size of the moon on the sky. So LOFAR provides us with a very large field of view, which is why it was designed this way, but why it becomes a problem for why satellites can become a problem, because this is a 1-hour observation, and all these orange and blue lines are satellites from the Starlink constellation that flew through the beam pattern during this 1-hour observation. And the plot on the right shows one of our detections where we can see that the red track from the predicted path of the satellite, the beams that the satellite passed through, they have a higher flux level due to the radiation emitted by the satellite. And that looks a little bit like this. This is the data for about 30 seconds for one of the 91 beams. frequency on the left axis, running from 110 to 188 megahertz. We see intended transmissions from digital radio, air traffic communications, and other services. But when satellites pass, and these are depicted by these gray bars when the satellite is in the beam of a station, and the red part when it's in this particular beam, we can see that there is a broadband emission over large ranges of frequencies, and we can even see some of the side lobes. I hope the screen you can see that as well. And also here there's some fainter emission at this part of the band. And so this is just the data in one single beam. We can correlate this with the Starlink satellites by making a plot like this, where we show the beams on the sky again, and then each beam has the time series around the predicted satellite path showing the flux level. And as the satellite moves through the beam, we can see that the beams that it actually passes through has these strong spikes, and the spikes move to the right as the satellite moves through the beam pattern. This was at a single channel at a frequency of 175 megahertz. But some satellites were a lot brighter. This one, for example, indeed, it's bright when it's in the beam. But as soon as the satellite enters the station beam, we see that in all beams, the signals goes up. So we basically detect this. It means that this satellite is so bright that we detect it as soon as it enters the station beam. So we can detect it with a single station. And to sort of characterize the observations that we've done, we've used the beams that the satellites pass through. So, for example, here we have about 11 beams that the satellite passed through. By averaging the data of those 11 beams, shifting the times for when the satellite passes through the central beam, we can make a plot like this, which again covers the whole frequency range, but now at the full frequency resolution and the full time resolution, around the predicted passage time of this satellite. And we can see that we detect a broadband signal at basically all frequencies. Sometimes it's a little bit weaker, sometimes it becomes brighter again. But besides the broadband emission, there's also narrowband emission. So here at 125 megahertz, we detect something that is 25% the system temperature of our telescope. We also see narrowband emission at 135 megahertz and 150. And again, this 175, and that even is so bright that it is as bright as the system temperature of the telescope. So that's extremely bright, but this is narrowband. So these are some of the properties that we saw with a lot of the satellites, and you can see also some narrowband structure here that is a little bit wider in frequency. And then there were other satellites that were at lower orbits that were even brighter, but that showed these comb-like structures. So at basically 50 kilohertz spacing, there's narrow peaks that cover this part of the band. They're less absent at the other frequencies. And the interesting bit is that for this satellite, the narrowband signals at 125, 135, 150, and 175 megahertz are absent. And if we combine all that for the 68 satellites that flew through the LOFAR beam pattern during this 1 hour observation, we basically make this plot where we have time on the horizontal axis for the full hour, frequency, and then we have the narrowband signals here in blue, purple, light blue, and orange. And then the size of the circle gives us the strength of the signals in Jansky. So at 175, we detected signals that go up to basically 500 Jansky in brightness. Same for the 125, that's a few hundred Jansky. And then for the broadband signals, we defined frequency ranges shown here in green, red, and purple. And there, the broadband signals are obviously weaker, but they still are a few Jansky in brightness. And as I said, we observed satellites at different altitudes. So there are the operational satellites, or at least satellites that we think are operational because they're at the 550 kilometer altitude, orbital altitude, and those are depicted with the solid lines. But there are also a train of Starlink satellites that had been launched a few weeks before this observation, and they were at 350 kilometer altitude while they were still raising their altitudes to the operational altitude. And of course, they were nearby, so we have higher sensitivity to them just because of distance squared. And they are depicted with the dotted lines. And we can see that basically the narrowband signals are absent for those, whereas the broadband signals are brighter. And well, the fact that the broadband signals are brighter, we just attribute to the distance being smaller. They're closer to us, so any intrinsic signal will be brighter at our telescope. But the absence of the narrowband signal we attribute to operational modes, that we think that these satellites are not yet operational and that these narrowband signals are related to something operational at the satellite. And so to conclude, we detect these narrowband signals, which can be very bright, up to 500 Jansky at 175 megahertz. They seem to be harmonically related, so 125, 150, and 175 megahertz could indicate that there is a 25 megahertz clock on board the satellite, of which we're seeing the harmonics. This signal is absent on the low altitude satellites, suggesting that those satellites are in a different mode, but we'll have to hear from SpaceX if that's indeed the case. And then the broadband signals, they're fainter, a few Janskys, but they're seen basically at all satellites, regardless of altitude and operational mode. And that the strength varies between satellites. So it may be some viewing geometry that changes from satellite to satellite. And then some of those also show this 50 kilohertz comb in this 150 to 180 megahertz frequency range. And these combs of narrow peaks, they are reminiscent of interference you see from power supplies. The DC-DC converter uses these switch mode power supplies that can give you this kind of RFI. And there was a recent paper published using using the engineering development array from the SKA in Australia, where at the SKA site they confirm signals within the broadband range that we detect. So these signals are present at other locations as well, especially also the SKA site, which of course has been chosen to be radio quiet, far away from human interference. But of course, now that we have these satellites constellations, yeah, they also will suffer from this unintended electromagnetic radiation. So what this means for LOFAR is generally an increased noise in all our observation. And the spectral structure due to the combs, that could be a specific problem for those science cases that want to look at high frequency resolution spectra to look at radio recombination lines. And some other science cases may be impacted differently than others. And that's something that we're still looking into. But the main worry is that these unintended electromagnetic radiation are not covered by the ITUR regulations, because those are specific to transmissions and probably do not apply to this radiation. And so for now, we are really relying on the goodwill of the satellite operators to make sure that their satellites don't leak this radiation and cause problems for astronomical observations. And we're working with SpaceX to understand what on their satellites causes this emission, and so they can look into what could be done to minimize this. And then with LOFAR, we're doing a survey of a larger set of satellites, Starlink, Space OneWeb, and also the Kuiper satellites when they're launched, to see if these also will emit UMR in the LOFAR band, but we're also looking at some of the other telescopes for other frequencies. And that's all I had to show today.
Thank you very much, Cees. I think unintended emissions are really a big issue. We have time for one question from the audience, if there are any. Yes, please. Microphone is coming.
Thank you, Gus. Very interesting. I have what I'm sure is a naive question. So as the unintended emission are expected to increase with the increase of launching and the population of orbits, I was wondering, is there any hope or any attempts to extract the astronomical signal from the frequency ranges affected by satellites, or is the expectation that those will not be useful anymore?
Yeah, I think that will depend on science case to science case. If I go back to this slide, I think the worst case we can be in with a telescope like LOFAR that has a large field of view per station is that as one satellite moves out of the field of view, another one moves in, and you get into this regime that all your data is affected. Until we're in that regime, we can proactively mask the data where we predict satellites to be in. But again, this may differ from science case to science case, and that's still something that we're looking into. Yeah, it's still an ongoing question how to exactly deal with this, and also how it spreads to frequencies below and above the range that we've looked at so far.
All right, thank you very much, Cees. I think there's going to be plenty more questions on Slack, and for the audience as well. If you don't get to ask a question here, please ask it on Slack.
Thank you.
Thank you.